Xiong. He works for Whamcloud. Take it away.
Okay. So thank you. This is my name, and in case for you guys have problems to pronounce my name, this is just a help information. Okay, so I'm going to talk about imperative recovery today, and let's finish it before the guys come into the room. Okay, so basically, first of all, I'm going to talk about a background on recovery. So we call it Recovery 101. And then I'm going to talk about a bit about why recovery is slow in current implementation. And then I'm going to talk how imperative recovery helps accelerate recovery process. And then finally, I'm going to dive into the implementation a little bit. Okay, so background on recovery. So as you know, Lustre is a distributed file system built on multiple nodes. And the nodes are interconnected by networks. The most popular network of Lustre would be InfiniBand. And also you can build your Lustre upon TCP/IP network, and this is good for test purpose. However, everything can fail in Lustre infrastructure. Node can fail because of power outage, and your disk can fail, and your disk controller can fail, and your network can be partitioned, and there are tons of bugs in Lustre implementation, and you may have seen a lot of error assert or error bugs. So this is annoying. So when we're talking about recovery, we are also referring to the process that bring the system into consistency again after the server is restarted. So this is the main purpose of recovery. Okay, so during the server failure time, the service can be interrupted. That means the applications can be returned with errors. It will just hang up for a couple of minutes. Depends on how fast your server came back to serve. And also during this time, POSIX semantics has to be maintained always. That means different clients have to see the same image on the same file. Recovery itself includes many stages. Connection recovery means the clients have to see the restarting targets in a limited time, and then do reconnection to the restarting targets. Transaction recovery means re-execute client RPCs and restore the system consistency, so as if the server was not restarted at all. Specifically, log is used to keep multiple nodes transactions in sync. For example, when you are deleting a file, you have to delete the objects on the MDT and the OST. And if the OST failed after you deleting the object on the MDT, and those objects on the MDT have to be deleted again after the OST is restarted. Okay, so let's investigate what makes recovery slow. This is because of two reasons, specifically in transaction recovery and connection recovery. So for transaction recovery, the server has to replay uncommitted RPC transactions from the clients. And those transactions has to be played in order when they were executed at the server side. This is done by transaction number. And also during this time, no new transactions can be accepted at the server side. This is because new transaction may update the status on the server, which can cause the replaying transactions can be finished correctly. Okay, so for transaction recovery, it means it has to wait all of the clients to reconnect to the server. This further means the server has to wait the slowest client to reconnect. So this is very bad. Another thing make recovery slow is the process for the client to detect the server death. Right now, the only way for the clients to know the server death is by the timeout of RPC. And this timeout has to be reliable because you have to consider about the network latency and the service latency, because for a busy server, the backlog of RPC queue would be very long. And also, you have to be, the RPC timeout has to be longer enough to distinguish a busy server from a dead server. You can worsen the problem if you are trying to reconnect a busy server. In case there's no IO RPCs in a specific time, PIN is used to detect the fate of a server. However, the problem of PIN is that it is not scalable. The number of PIN RPC is increased by the system size, that is the number of servers times the number of clients. However, the network bandwidth is not scalable. So if your system gets really large, the bandwidth consumed by PIN RPC is significant. So in one of our customer sites, the PIN RPC mostly can consume 20% of your network bandwidth. The only way to solve this problem is to increase your PIN interval. So because of this, a client may know the server failure after the PIN interval plus RPC timeout. So this is quite a long time. Mostly it means 10 minutes or 20 minutes. So, how can we get a fast recovery with this? So we need change. Okay, so we know the problem and we solve it. And we add value to Lustre. So this is imperative recovery. I'm going to use IR to stand for it. So IR can accelerate reconnection by notifying the clients of server restarts, no longer use timeout. MGS is used to reflect the server failure events to the clients. This is because when a target is restarted, it will register itself to the MGS so that the MGS knows the server failure anyway. And also, after the client is notified, it will do reconnection to the restarting servers. Imperative IR depends on MGS right now, so it is a best effort service because the MGS can be down. This means we are not going to take the place of standard recovery right now, and it is also important to identify which target which version of target the client is currently connecting to, because standard recovery may restore the connection and may finish the transaction to the restarting target before IR gets involved. So it's very important for this. And also, IR is going to support failover server. That means if the target is restarted on a new server with new NID, IR has to handle this case and reconnect to the new server. Okay, so let's talk about a bit about implementation of IR. So the most important component in the IR is target NID table. This table will record which NID the targets are living on, and whenever the MGS receives a message, it will update, it will change the table. Also, there is an DLM resource defined for each running file system on the MGS, and we have a log for this resource. This is because the client will cache the NID table on client side, by holding the shared mode of this log. In this way, when the MGS update the table, it will enqueue an exclusive log so that the clients can be notified about the change. And then client will fetch the NID table from the MGS and then update its local cache. And then, because after the clients get the NID table, it will have the new NID to the new target, to the restarting target, so that it can do reconnection. Okay, so this diagram demonstrates the the process of imperative recovery. So just take a look at it. I don't have a laser pen. Oh, yeah. Okay, so the after the target is restarted, it will register itself to the MGS, and MGS will notify clients, and the clients get the information from the MGS, and then do the connection. So the whole process is very clear and simple. Okay, so let's talk about the implementation of target NID table. Target NID table is versioned, and the version number is increased by 1 whenever the table is changed. And the latest version has to be written into persistent storage. This is because the client can be confused if the MGS is restarted. Also, clients cache the target table, NID table, with the version number. Each living target has an entry in the table, and the following information must be included in the table: target name and target server index, and the number of NIDs and then NID list. Because we are going to support TCP6, IP6, so 128 bytes will be assigned for each NID. Also, we have to include the table version number when the entry was last updated. And then the last one is target instance number. This number is uniquely generated by the target when it is started. Okay, so the NID table may be large. So this is because in a large cluster with 1,000 targets, it's impractical to transfer the whole table in one RPC. So this is because you can count how many bytes is needed for the whole table with 1,000 targets. So for performance reason, only updated entries will be transferred. How can we do that? So the MGS maintains the table in a linked list with the increasing version number of the entries. And when we are syncing the table between the clients and the server, the clients will provide their cached version number to the target to the MGS, so that the MGS will find out the difference between these two versions, and then we are just only return the entries which has been updated during these versions, and then those entries will be transferred to the clients. Okay, so this diagram demonstrates the main process of handling the transfer updated NID table. Thank you. Okay, so at initial time, the client version is in sync with the current version. So this is the latest version of target NID table, and the client is in sync with this version. And the NID table is a linked list with the increasing version number of each entry. Okay, so let's assume that the target 0 is restarted, so that the table version is increased by 1. So now is the current version plus 1. And then the entry of target 0 is moved to the end of list, because we are maintaining the list by an increasing version number. And then the client will be notified. Okay, so the client will provide its version number. So this is the client's version number to the MGS, and the MGS will find only target 0 is changed during between these two versions, and then target 0's entry will be returned to the client, and finally the version will be synced again. So let's assume that there are multiple targets are restarted during this time. So there are more entries at the end of the tail, at the end of the list. And the client will get multiple entries once. Okay, so this is a glimpse of imperative recovery, and there are some problems with current architecture. First of all, MGS is a single point of failure. If the MGS is down, IR won't work anymore. But standard recovery is not affected. So 99% we can do fast recovery, but in case the MGS is down, you are back to the old time, and have to bear with long recovery time. But this problem can be, you can separate the MGS and the MDS, and because the code on MGS is simple, so maybe in this way you can make MGS live longer. And another problem is the scalability problem. If the class becomes really big, but how big is really big? I do not have any idea. So, for example, 100,000 clients. So it would be very slow for the MGS to notify clients one by one. This is because MGS needs to send 100,000 RPCs to notify clients, and the clients have to fetch update of entries with 100,000 RPCs as well. Sorry,
Why do the entries going to the clients have to have all the names for all the clients?
yeah, basically, well, so right now we still use configuration log when the client is restarted, when the client is mounted, right? And only when the target is restarted, we're going to transfer the new NIDs that the target is running on to the client. So sorry, I do not quite understand you. So can you please repeat again?
The second goal of client fetch update entries with 100K RPC total.
In total, yes. This is because you have 100,000 clients. Yes, each client has to send at least one RPC to fetch the update entries. I'm sorry, okay.
100K RPCs are not 100K size RPCs, they're just 100,000 RPCs.
Yes, the number of RPCs. It's not the size of RPCs. And they also have overhead of queuing the recover log. So sooner or later, if your cluster becomes huge, you will have scalability problem because it will be an impossible mission for the MGS to notify clients one by one. Okay, so we have solutions, of course. For example, as Eric Barton just presented, Health Network is a good solution for the scalability problem. And also, we can have MapReduce algorithm on the MGS. So this is great. Let's take a look at it. So instead of the MGS notify the client directly, we can use the arriving targets as intermediate nodes to notify the clients, so that we can split the clients into subset, and by some rules, let the specific targets to notify one subset of clients, and then the clients will reconnect to the target. Of course, the MGS will monitor the process of each target because the target itself may be dead during the notification process. So we have to reassign the task to living target again. Okay, so imperative recovery is still in progress, and we are planning to release it in the Q2 of 2012. This project is sponsored by Oak Ridge. Thank you, guys. You give me the job. Thank you, Whamcloud. Okay, thank you. So if you have any questions, please speak it out slowly and clearly. Thank you.
Hi, so for future work, have you given any consideration to the problem that servers have where clients aren't necessarily going to reconnect?
Yeah.
Recovery can also be delayed. Even if you have 100,000 clients connecting into a server, there may be situations where clients, clients because you have a health network, can't reconnect. Are you planning to take advantage of that?
I can hear. Can you please shorten your
Sure.
questions?
Have you given thought to short-circuiting the server recovery where clients have failed and cannot reconnect?
Yeah.
We can talk offline.
I don't get your point.
So the recovery process is hung while all of the clients attempt to reconnect to that server.
Yeah.
And the server has to wait for every single client to reconnect before replay can begin. If you have a health network, you may know in advance that certain clients will not reconnect and therefore can begin
Yes.
recovery with version-based recovery immediately. Are you
Yes.
planning to do that?
Basically, so there's a problem in your questions itself. So the server will not wait for all clients, to reconnect, to replay the transactions. If the next transaction number is in the queue, it will re-execute it immediately. And also about your second question, about health network. Yeah, I think so. Yes, in this case, health network will detect the dead clients immediately, and so that the server will be notified that don't wait for this client anymore. Yes, so it can shorten the recovery window a little bit.
Thank you.